Okay. All right. Hello, everyone. So let's start the afternoon session by talking about distributive subtyping with finitary and infinitary unions and intersections. All right. So please interrupt me if anything is unclear. Right. I think we have time, right, for some questions, including during the talk. So intersection and union types. How many of you are familiar with intersections and unions? Maybe, yeah? It's getting pretty popular, right? So you have intersections of the form S and T, or S intersected with T, which represent types that contain the values of both S and T. You also have union types dually, right, for types that contain values that are either in S or T or both. And sometimes in math notation, we use this square cup and square cap notation to denote that this is an algebraic operation. It doesn't necessarily correspond to a set intersection or a set union, but more like an algebraic operation. And in languages, in actual programming languages, we use the ampersand and pipe characters. So here's an example in many languages with intersection types that also have record types, such as this record type, which is a record of field A of type S and field B of type T. Then that record would be a subtype of the intersection of the records made of each individual field, right? And this means that basically the record type can be thought of having both the type, just a record of A with type S and a record of B with type T, right? This is thanks to record width subtyping, the fact that you can forget some of the fields of a record by upcasting. And as for an example of unions, you could have a union if you have a branching statement, for example, that returns two different values in each branch, one different value in each branch. And if these two values don't have exactly the same type, then you may get a union type as a result. So here you have a value that could be either foo or bar at runtime. Okay, so here's my question. Should intersections and unions distribute over function types? And if so, how? Okay, so let's look at an example and let's vote. So for example, this general intersection of two function types from S to T and from U to V, can we say that it's equal to a function type even when the types don't match, right? If S is not equal to U or T is not equal to V. So who think this cannot be done? There should be no distributivity. Okay, so one thing we can do that's kind of obvious in a way is that you can say that if the parameters are the same, then the result can be then you can distribute the intersection into the result, right? So if you have a function that gives us a T when you give it a S, and it also gives us a U when you give it a S, it kind of makes sense to say that after you give it an S, it gives you both a T and a U, right? Kind of. It depends, right? It might be sound in some systems and not in others. Raise your hand if you think this looks good. Wow, nobody. One person. Okay. So actually, this doesn't really work in the presence of side effects, but that's another story. How about same results? If you have this intersection, you can say that, well, in practice, it means the function, you can give it either an S or a U, right? It doesn't matter. And it will always return to U or T. So raise your hand if you think this should be done. Yeah. Sure, it makes sense, right? This one does make more sense. How about full distributivity? That's if you have arbitrary types in the two function types, you can actually distribute the intersection into a union on the left and an intersection on the right. That's weird. Who thinks that can be done? Nobody? I think it can be done, okay. There's also ways of saying that, well, actually, you can equate the intersection to the function type where you have intersections on both sides. And in fact, so this one is a subtype of that one, right? But you don't have the subtyping the other way, using the normal function subtyping rule. But it is possible to decree by fiat that these two types are actually the same type, right? They're equivalent. And similarly, you can also do it with a union. It also holds in one direction, but not the other. And you can decide in some systems that actually it holds in both directions as an axiom. So there are many, many options, right? So which one should you pick? And the answer is that there's no right answer, and it depends on the context. It depends on your language. And here's a quick overview of what languages do. So actually, both Scala and Ceylon have full distributivity, the weird rule I showed that distributes into unions and intersections. Okay? TypeScript doesn't actually do any distributivity, but you have things like CDUs, which use set theoretic types. I'm going to explain a bit later, which does distribute when both parameters or both results are the same, but doesn't do full distributivity. Okay? And some historical language, like research language, like Foresight, which does also something similar. So how come, right? Well, first let's look at some examples. So in TypeScript, you don't have any distributivity. So actually, it takes the first option. And actually, in TypeScript, you cannot really say anything because unions are just weird. They're not commutative, right? You cannot swap the components of a union and have the program still type check in all cases. So maybe let's not talk about TypeScript. Let's talk about a more serious language with similar capabilities. And this would be, for example, CDUS, the language with semantic subtyping, where every type is really thought of, or really formalized as a set of value, an actual set of the values that inhabit it. And there's no general distributivity of intersections over arrows, but you can distribute them when the parameters or result are the same as I mentioned. So if you represent this visually, it's like, yeah, you have these two types, and then their intersection corresponds precisely. So the intersection of the corresponding sets of values corresponds precisely to the intersection type in semantic subtyping. Okay, so that's just a graphical, visual way of seeing it. And so in Scala 3 and Ceylon, as I mentioned, you have full distributivity, you have this rule, okay? And how could that be? Because after all, think of an intersection of concrete types, int to int and string to string. Scala and Ceylon tell us this is the same as int or int to int and string. So a function that takes int to ints and strings to strings, meaning it has this intersection type, also returns a value that is both when given either. Weird, right? And so it turns out that this is actually sound in many cases. And in this particular MLstruct core language that we designed in our research group earlier, we do use the full distributivity, and it's actually crucial in having principal type inference, because if you cannot do that, then you cannot reduce some awkward constraints and without having to do some backtracking, and you cannot achieve principal types. So there is very important. But then we generalize our system by adding more powerful types, including first-class polymorphic types. So decidability goes out of the window, and you don't really have complete principal type inference anymore. But you have very powerful types like for A to A, okay? And with polymorphic subtyping, so for example, you can upcast this for all type into a normal type, right, by instantiating it. The problem is that this is no longer compatible with full distributivity, okay? Because this type, this for all type, you can instantiate it into both sides of this intersection, and so by the definition of intersections, it means that the type is a subtype of the intersection, and clearly this is not the same as this, right? And so we have to avoid it in this case. So basically, you can think of the ML's struct approach, the previous one, as having a simpler lattice of types, and intersection corresponds to picking the meat in that lattice, and there's no polymorphic types in the lattice, and so it happens that it's perfectly fine to pick that type as the meat. But here it's no longer the case. But still, it's not really clear what you should actually do in practice and what are the implications. So there are also other approaches like compositional programming, a research language, where intersected function types decay into intersections on both sides. It's fine. And for size, as I mentioned before. A related issue is, how about arbitrary type constructors like class types? What if you have C of int intersected with C of string? Do you have C of int and string? Not in general, right? But what if C is covariant? Is it the case? It's not actually clear, because even in Scala, which is implemented like that, if C is covariant, then you can distribute the intersection inside. This is not really completely clear, right? It's not actually justified by the theory of Scala. You would have to add new axioms to support this. And so this is currently an open issue in Scala, right? There's an issue in the bug tracker. People don't really know, is it really good to do, fine to do that or not? And as we've seen, it's not quite clear when you cannot do that. So first, let me give some background on unions and intersections, just to make sure we're on the same page, a little bit more formal background. So intersection types, they can be summarized in this short slide as the following typing rules. So this is mostly slightly reformulated rules than the rules given by Copo and Desani Ciancaglini in 1980. So what these rules say is just that well, you have the normal rules for functions and applications, and then you have intersection introduction, where if some term T can be typed as T1, and it can also be typed as T2, then you can type T as the intersection. And then you can eliminate the intersection. If you have actual values with the intersection, you can pick one of the two, depending on which you want to use for this particular use site. Okay? Now you can generalize this notion to subtyping. Yeah, let's first talk about subtyping like this. So in 1983, BCD subtyping was proposed, which stands for the initials of the authors. And this is basically a way of making subtyping aware of intersections, so that you can have these kind of coercions at the type level. Right? So intersections are idempotent, so you can take a T and make it an intersection of T and T, and you can eliminate, forget about some components of it through subtyping, and you can apply subtyping concurrently inside the intersection, right? And this system did have this bit-fishy rule that distributes the intersection inside, which is not sound in the presence of side effects in a system like this. Okay. And so, an interesting view of subtyping, I think it's useful for the intuition how to interpret subtyping is as retyping. So the normal subtyping rule that most systems have is that if you have a term T of type S, and you know that S is less than T, then the term T also has type T, right? Capital T. But how do you define subtyping, and which subtyping relations should hold? And I think it's useful to think of subtyping as basically a no-op coercion, right? So a coercion that you can do very easily by just reinterpreting the term, by just retyping the term. So you can add a rule that conceptually represents what subtyping is. Subtype, S is a subtype of T. If, assuming some variable X has type S, you can conclude that the same variable has type T. So that's just one way you can conceptualize subtyping as a retyping. And if you do that, then you can actually derive all of these rules, all of these intersection subtyping rules from the original intersection typing rules, along with a rule for introduction of top types, right? So just using normal typing rules, which are kind of simpler, you can derive all of these thanks to retyping. So that's pretty cool. Another thing that I want to emphasize is that the intersection introduction rule is not necessary to support in full. So as a reminder, let me just quickly recap it. Intersection introduction says that any term T, if it can be typed independently at type T1 and T2, can then be typed at the intersection of T1 and T2. But actually, it's a very powerful rule. It makes intersection type system basically undecidable because it makes well-typedness equivalent to strong reduction, to strong normalization, right? So it's too powerful, but it's possible to avoid that very general rule and instead use more specific rules. And as an example, in TypeScript, this doesn't actually hold. Like if you have, let's see, so you can type a function, a lambda from A to A as both number to number and boolean to boolean. Independently, you can do that, that's fine. But you cannot type it as the intersection. So that demonstrates that in TypeScript and similar languages, you actually do not have general intersection introduction. But what you can do in TypeScript is that you can define overloaded functions using function signatures like this, and that's basically that acts as one very specific kind of intersection introduction, specifically for functions, right? And so what you do is that you provide declarations that are more specific, and then a less specific implementation where if you want to type check it, you have to use less specific types inside, right? And you may do some pattern matching or some tests inside to determine in which case you are. And then TypeScript will type check that the function can be given both signatures independently. And thanks to this, it will allow you to say that the function has the intersection type of these two things, right? Everything clear so far? So that's for intersection. Now for union types, which are introduced a bit later than intersection types, but still a long time ago. You have also union introduction, union elimination. The elimination rule is a bit more complicated. There's no need to go over it. What's interesting to know is that, again, you can derive subtyping from the typing rules using just retyping. And so the subtyping looks like this for unions. It's completely dual to intersections, so no surprises. In their paper from 1995, where they present subtyping for union types, Barbanera et al. Also proposed a distributivity for function types, right? So if you intersect these two function types, you get the one that I showed before. When the result types are the same, you can distribute the intersection into a union in the parameter. So there's been a recent resurgence of interest in both academia and industry for these types, right? Intersections and unions, which is why most of you already have heard of them. Okay, and moreover, most type systems with intersections and unions distribute one into the other, right? So this is not actually problematic, but just as a side note. And so I mentioned that I wanted to talk not only about finite intersections and unions, which is what we've seen so far, but also infinite or infinitary unions and intersections. Basically, you can think of for all types and existential types as infinite intersections or infinite unions, right? So for A, f of A is the same as f of int and then string and blah, blah, blah. So if you have a polymorphic function that for any A takes an A and return an A, then it's really the same as a function that can take any particular type. Like when given an int, it gives you an int. When given a string, it gives a string, etc., right? And the neat thing about this is that you can use the same reasoning principle that you use for normal unions and intersections and lift them to the infinitary setting most of the time, right? Okay, so finally I come to the meat of the talk, which is my argument that you can elucidate the difference between these different distributivity rules as the divide between church and query-style semantics. So as a reminder, church-style semantics says that the terms you're manipulating are internally typed. They have a type, the function parameters have a type, and so it's always known what's the type of things, and the semantics is given on these internally typed terms, right? Whereas in query-style semantics, the types don't matter for the semantics of the term. All terms have semantics, even those that don't have a well-defined type. And you typically provide types externally. On the existing term, you say, oh, this particular term has this type. And you use types to prevent, you use types to exclude terms that misbehave, right? Terms that do bad things like crash. And so basically, you can think of intersection-based overloading as fundamentally query-style, right? Remember the intersection introduction rule. It said that you needed to type the same term as two completely different types at the same time, right? Simultaneously. And this is why this is a query-style language feature. It asks you to not have any internal type, but to consider that the term can have many different unrelated types at the same time. Okay, and this fits particularly well for TypeScript, right? Because TypeScript is just JavaScript with types given externally, but actually the semantics is given by JavaScript itself. You can just erase the types immediately, and the types don't participate in the semantics at all. Whereas a language like Scala is query-style. So in Scala, the lambda term x to x doesn't mean anything on its own, right? And if you write it as part of a bigger expression, like list of 123.map of x to x, then the compiler automatically elaborates this implicitly to a fully internally typed term, right? Where the parameter type is given. And only terms that have these types have semantics. Otherwise, they just cannot be compiled, you know? And so such a given lambda term cannot have multiple unrelated types simultaneously. It's a church-style language. So how does church-style explain full distributivity? Now we can actually justify this crazy rule I showed earlier that didn't seem to make any sense. But actually, it makes sense. So think of it this way. Any function that you have in Scala, call it f, right? That happens to be found to have both types s to t and u to b. So somehow you know that the f has both types. So it also has the intersection type, right? S to t intersected with u to b. Then since it's a single value, and values cannot have multiple unrelated types at the same time, there must exist one single domain and one single codomain that describe this function, right? And both S and U must have been obtained by narrowing this original domain D, right? Through function covariance. So for example, if you have a function that says that goes from object to object, you can narrow that to a function that goes from int to object or string to object, right? And similarly for the codomain, right? There's only one true codomain for the function, but it may have been widened into these other T and B types, right? And so, so we must have the following subtyping relations, which allows us to justify this, the rule that says that this function f, okay, which has type D to C by assumption, also has type union of S and U to intersection of U and V. Do you see where I'm going with this? So I think that's the reason why full distributivity is fine in Scala. and not in a language like TypeScript where it's wildly unsound, right? You can also generalize this reasoning to arbitrary class constructors, such as the class for functions. So in Scala, functions are not really primitives. The primitives are classes, and functions are just one particular type of class. So the function of one argument, the type of functions of one argument is represented by the abstract class function1. And in the standard library, function1 takes two type parameters, but in terms of foundations, Scala is defined in terms of dependent object types calculus. And in this calculus, you don't have actual type parameters for classes. These are syntax trigger for type members. So it's like you have types inside the class, the abstract class, and they're not defined. They don't have a given value. And moreover, you have a method apply that corresponds to actually calling the function. And so this, on one hand, is how Scala represents functions. And on the other hand, the dependent object types calculus treats objects as basically records of both values and types, right? And if you remember the idea that you can derive subtyping rules through retyping and some form of eta expansion, that was the case for function subtyping. Well, consider that you can also eta expand records, right? So if you have the following record that has type T, you can where each label, each field is taken from an existing term T, projected to the field of the same name, right? Then you can tell that the term T has type capital T. So that's eta expansion for records. And if you accept this eta expansion for records, and if you also accept retyping, the rule I gave to derive subtyping relations, then you do again get full distributivity of constructors, of class constructors. Okay, so I don't have time to go into the details. You have to trust me on this, but we can talk more about it separately. All right. So let's conclude quickly. I tried to in this talk examine the problem of distributive subtyping from first principles, going back to the roots. What are intersections, unions, and how to interpret subtyping in a way that subtyping between these type forms can be justified intuitively. And I tried to explain that the differences in distributivity between different languages actually comes from the church and curry style divide between the two styles of semantics. Okay, and that's why some rules may be completely unsound in one language, but completely fine in the other, right? Okay, so thanks. That's it. And do you have any questions?
Yeah, thank you. Nice talk. So, as somebody who's delved into the specific things, if you were to design a language, which typing system would you pick?
I think it depends. I think both have pros and cons. Currently, we're designing a language called MLsub, which has curry-style semantics. And so we also want first-class polymorphism, which is another thing I didn't actually explicitly mention, but if you want first-class polymorphism, you have to use a curry-style language, basically, right? If you want polymorphic subtyping. And so for this reason, currently we are using curry-style. But I think it also makes sense to do what Scala does and do more magic at compilation time based on the types. That can also be very useful. Yeah. So, not sure.
I see. Very cool. Thank you.
Thanks. Any other questions? Okay, so if not, let's move to the next talk, because it's time. So next. next